Imagine you're watching a friend fall toward a black hole. Not a metaphor. Actually watching through some impossibly powerful telescope as they drift closer and closer to the edge. Here's what you would see. They would slow down. Not gradually, in the way a tired swimmer slows near the end of a lap. Fundamentally, physically, permanently. Every movement they made would take longer. Their arm lifting in a wave would stretch into minutes, then hours, then years of your time. The light leaving their body would shift. First slightly orange, then deep red, then into wavelengths invisible to the human eye, frequencies stretching as gravity bent the signal on its way out. And then, right at the edge, the exact boundary where escape from the black hole becomes impossible, they would freeze. Completely. Suspended. A photograph of a person at the threshold of the most extreme thing in the universe, held in place forever, never crossing, never arriving, never disappearing. You would never see them go in. Now here's the part that should break something in the way you think about reality. Your friend would have a completely different experience. From their perspective, falling toward that same edge, nothing dramatic would happen at the moment of crossing. No wall, no barrier, no flash of light announcing the point of no return. Time for them would flow normally, seconds feeling like seconds, thoughts following thoughts at the usual pace. They would cross the boundary and continue inward, unaware that from where you're standing, they stopped moving 1,000 years ago and have been suspended at the edge ever since. Same event, same physical location. Two completely irreconcilable experiences, and both of them are correct. That's not a paradox in the sense of an error in the physics. That's what the physics actually predicts. Two people, in the same region of space, experiencing time so differently that one crosses a threshold and one watches the other freeze forever at it. The universe permits this. The universe does this. And understanding why requires dismantling a belief so embedded in everyday experience that most people never notice they hold it. Time is not constant. Right now, as you watch this, time is not passing at the same rate everywhere on Earth. It's not passing at the same rate on the floor of this room as it is at the ceiling. It's not passing at the same rate for a person sitting at sea level as for a person standing on top of a mountain. These differences are real. They are measurable, they are happening right now, and they are not random. They follow precise mathematical rules that Einstein worked out over a century ago, and that every physicist who has tested them has confirmed, over and over, with increasing precision. The idea that time is fixed, universal, and identical everywhere is not a scientific conclusion. It was an assumption, a very reasonable one, given that the differences in everyday life are too small to detect without extraordinarily sensitive instruments. But it was always just an assumption, and it turned out to be wrong. Let's build this understanding from the beginning, because it earns everything that comes after it. In the early 1900s, physics had a serious problem. The equations describing light kept producing an uncomfortable result. The speed of light appeared to be constant, regardless of how fast the observer was moving. This wasn't supposed to happen. Common sense and the physics of Newton said that speeds add. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, someone standing beside the tracks sees the ball moving at 150 kilometers per hour. Speeds stack. That's how everything in everyday life works, but light doesn't do this. Every experiment designed to detect differences in the speed of light based on how fast the detector was moving kept returning the same number, about 300,000 kilometers per second, regardless of the detector's motion. Whether the detector was moving toward the source of the light or away from it, at whatever speed the experimenter could achieve, the measured speed of light came out the same. Einstein's insight, the one that reshaped all of physics, was to take this result seriously, rather than treating it as an error to be explained away. What if the speed of light is genuinely constant? What has to be true about the universe for that to be possible? The answer he arrived at was that space and time are not independent fixed backdrops. They're flexible dimensions that adjust themselves to keep the speed of light constant for every observer. If you're moving fast and you measure the speed of a light beam, space contracts in your direction of motion, and time dilates, slows down, in your frame of reference, in exactly the right amounts to keep the number you measure equal to 300,000 kilometers per second. Time dilation isn't a side effect or an approximation. It's the mechanism the universe uses to keep the speed of light constant. The faster you move, the more time slows down for you relative to a stationary observer. This is special relativity, and its predictions are so precise and so consistently verified that it underpins almost everything in modern physics. Now, there's a thought experiment that makes this viscerally clear, and it's one that trips people up when they first encounter it. Imagine two identical twins. One stays on Earth, the other boards a spacecraft and travels to a distant star at a substantial fraction of the speed of light, then turns around and comes back. When they reunite, something strange has happened. The traveling twin is younger, not just slightly younger, depending on how fast they traveled and how far, potentially years or decades younger. Their biological clock ran slower during the journey. They experienced fewer heartbeats, fewer breaths, fewer seconds. The twin on Earth aged normally. The traveling twin aged less. This is called the twin paradox, though it's not actually a paradox. It's a real prediction of special relativity that has been verified experimentally in a rougher form. In 1971, physicists Joseph Hafele and Richard Keating flew very precise atomic clocks around the world on commercial airplanes, east-west and west-east, and compared them to reference clocks that stayed on the ground. When the airborne clocks returned, they showed different times than the ground clocks, in directions and amounts that matched what relativity predicted to within the margin of experimental error. Atomic clocks in airplanes, not spaceship travel at near light speed, not science fiction. Commercial aircraft, moving at a few hundred kilometers per hour, carrying clocks sensitive enough to detect the tiny time dilation their motion produced. The effect was real, measurable, and exactly as Einstein's equations said it would be. 10 years later, Einstein extended his theory to include gravity, and the result was even more profound. Special relativity dealt with motion through space. General relativity dealt with the nature of space and time themselves, and what mass does to them. Gravity, Einstein proposed, is not a force in the traditional sense. It's a curvature. Mass curves the fabric of space-time around it, and what we experience as the pull of gravity is simply the tendency of objects to follow the straightest possible path through that curved geometry. The Earth doesn't attract the Moon by sending invisible tendrils across space. The Earth's mass curves the space-time around it, and the Moon follows the curve. One of the consequences of space-time curvature is that time runs at different rates depending on how deep you are in a gravitational field. The stronger the gravity, the more curved the space-time, and the slower time flows relative to a region with weaker gravity. This isn't an analogy. It's a direct prediction of the mathematics of curved space-time, and it's been confirmed with extraordinary precision. The most everyday example, and arguably the most striking one, is GPS. The satellites in the Global Positioning System orbit at roughly 20,000 kilometers above Earth's surface. At that altitude, Earth's gravity is noticeably weaker than at the surface. Weaker gravity means less curved space-time, which means time runs slightly faster there than it does on the ground. The difference is about 45 microseconds per day. That number sounds trivially small. What it produces, if left uncorrected, is navigational drift of around 10 kilometers every single day. A GPS system that ignored Einstein's time dilation would be useless within hours. It would be directing drivers into fields and over cliffs. Every GPS satellite carries software that constantly adjusts for this relativistic effect. running its clock slightly slower to stay synchronized with ground-based reference clocks. The phones in every pocket on the planet navigate correctly because engineers accounted for the curvature of space-time in the satellite clocks. Relativity runs on your phone. Time dilation is not a theoretical curiosity. It is infrastructure. Now take this to its logical extreme. The GPS effect is small because Earth's gravity, by cosmic standards, is gentle. Moving toward a stronger gravitational source, a denser, more massive object, amplifies the effect. Near the surface of a neutron star, a collapsed stellar remnant so dense that a teaspoon of its material would weigh roughly 1 billion tons on Earth. Time dilation becomes dramatic. A clock at the surface of a neutron star would run measurably, significantly slower than a clock orbiting it at a safe distance. Someone living on the surface, an impossible scenario biologically, but a useful thought experiment, would age noticeably slower than someone in orbit above them. Push the density further. Compress more mass into a smaller volume. Eventually, you reach the point where the gravity at the surface becomes so extreme that even light can't escape. And when light can't escape, nothing can, because nothing with mass can move faster than light. At that point, you have a black hole. And the gravitational time dilation doesn't just become severe. It becomes, at a specific surface, the event horizon, infinite. Infinite time dilation means, from outside, time appears to stop entirely. That's the physics behind what you'd observe watching your friend fall in. Their clock isn't running slowly. At the horizon, from your perspective, it stops. The frozen image is not an illusion or a visual trick. It's the real physical consequence of infinite gravitational time dilation at a surface that general relativity predicts and observations confirm. The strangeness doesn't end at the horizon, though. It begins there. Before going any further, let's be precise about what an event horizon actually is, because the common image of it as a glowing ring or a visible boundary or a physical surface you could touch is misleading in ways that matter. A black hole forms when a massive star, typically at least 20 times the mass of our Sun, exhausts its nuclear fuel. For most of a star's life, the outward pressure generated by nuclear fusion in the core exactly balances the inward pull of gravity. It's a continuous equilibrium, maintained across millions or billions of years. When the fuel runs out, that balance collapses. Gravity wins, instantly and completely. The core implodes in a fraction of a second. The outer layers bounce off the collapsing core and explode outward in one of the most energetic events in the universe, a supernova. What remains at the center, if the original star was massive enough, is a black hole. The collapse compresses the mass into an extraordinarily small volume. How small? The mathematics of general relativity produces something called a singularity, a point of zero size and infinite density. Though whether this reflects physical reality or simply the limits of the theory is an open question. What's important for our current discussion is not the center, but the boundary, the event horizon. An event horizon is not a physical surface. There's no membrane, no edge you could stand on, no boundary you'd feel with your fingertips. It's a mathematical surface, a threshold defined by a single question. Can light escape from here? On one side of the horizon, the answer is yes. Light emitted in any direction will eventually reach infinite distance. On the other side, the answer is no. Any light emitted there, in any direction, curves back inward under gravity. The event horizon is precisely where the answer changes from yes to no. Nothing marks it physically. It exists only as a geometric feature of the curved space-time around an extremely dense mass. The radius of a black hole's event horizon depends on the mass. For a black hole with the same mass as our Sun, the event horizon would be roughly 3 kilometers in radius, the entire mass of a star compressed inside a sphere about 6 kilometers across. For the supermassive black hole at the center of our galaxy, Sagittarius A star, with a mass roughly 4 million times that of the Sun, the event horizon is about 12 million kilometers in radius. For context, the Sun's radius is about 700,000 kilometers. The event horizon of our galaxy's central black hole is roughly 17 times larger than the Sun. Now let's go back to your friend and the two perspectives, because this is the heart of what makes black holes so philosophically destabilizing. You're watching from a safe distance. Your friend is falling freely, not fighting the gravity, just letting it carry them. From your position, light emitted by your friend has to travel outward, climbing against the gravitational pull of the black hole to reach you. The deeper in the gravitational well that light originates, the more energy it loses climbing out. And light pays this energy cost by stretching its wavelength. Short wavelengths, which carry more energy, become longer wavelengths as they lose energy to gravity. This is called gravitational redshift, and like time dilation, it's been measured here on Earth. In 1959, physicists Robert Pound and Glenn Rebka measured the gravitational redshift of gamma rays traveling from the basement to the roof of a building at Harvard University, a height difference of about 22 meters. The result matched the prediction of general relativity with an accuracy of about 10%, later refined to 1%. A 22-meter height difference on Earth produces a measurable frequency shift. Near a black hole, where the gravitational gradient is incomparably steeper, the shift becomes extreme. As your friend falls toward the event horizon, the light reaching you from them is increasingly redshifted, shifting from visible light to infrared, then to radio waves, then to wavelengths so long they become effectively undetectable. Simultaneously, gravitational time dilation means your friend is emitting that light more and more slowly from your perspective. Fewer photons per second, each one carrying less energy, arriving at increasingly long intervals. They don't disappear in a flash. They fade and slow, approaching a kind of asymptotic stillness, getting closer and closer to frozen without ever quite getting there, because time dilation is approaching infinite at the horizon, not jumping to it in a single step. The last photon you'd receive from them was emitted just before they crossed the horizon. That photon carries the image of your friend at the closest moment to the edge from which light could still escape. It takes an arbitrarily long time to reach you, stretched and faded, but it arrives. Every subsequent photon, emitted from inside or at the horizon, curves back inward and never reaches you at all. From your perspective, they're frozen there, not gone, not destroyed. Frozen at a moment just before the crossing, preserved in an increasingly faint and red image that technically never fully disappears. It just becomes too dim and too stretched to detect. Now take your friend's perspective, because this is the part where intuitions tend to break down most completely. Falling freely in a gravitational field produces what Einstein called an inertial frame. In free fall, you don't feel the pull of gravity. Astronauts on the International Space Station experience this continuously, floating inside the station because they and everything around them are falling at the same rate. From inside a freely falling frame, the local physics looks identical to the physics of empty space. There's no experiment you could perform inside a closed box that would tell you whether you're in empty space or in free fall near a massive object, as long as the gravitational field is uniform enough across the box. This is the equivalence principle, one of the foundational ideas of general relativity. It means that for your friend, falling freely toward the black hole, the local experience at the moment of crossing the horizon should feel unremarkable. No wall, no dramatic discontinuity. The space-time geometry at the horizon, from inside an infalling frame, is locally smooth. It doesn't have a sharp edge that announces itself physically. For large black holes, the supermassive ones at the centers of galaxies, or even stellar mass black holes much more massive than our Sun, The event horizon is large enough that the tidal forces at the boundary are gentle. Tidal forces are the difference in gravitational pull across an extended object. The fact that the gravity pulling your feet is slightly stronger than the gravity pulling your head when you're falling toward something. For enormous black holes, this difference at the event horizon is small enough that a human body would survive crossing it intact. Your friend, falling into a supermassive black hole, would cross the event horizon without any physical sensation marking the moment. Time continues flowing normally for them. The crossing is invisible. For smaller black holes, the stellar mass ones formed from ordinary star collapses, the event horizon is much closer to the singularity, and the tidal forces ramp up far more steeply. Well before reaching the horizon of a stellar mass black hole, the gravity pulling your feet would be so much stronger than the gravity pulling your head that the difference would stretch you lengthwise while compressing you sideways. Physicists describe this with the deliberately vivid term spaghettification, the process of being stretched into an increasingly thin stream of matter by tidal forces. For a stellar mass black hole, this would happen at a significant distance above the horizon. For a supermassive one, you'd cross safely through the horizon first, and only encounter the fatal tidal forces much deeper in, closer to the singularity. So, you watching from outside, your friend frozen at the horizon forever. Your friend, from inside, crossing without incident and continuing inward. Both physically correct, both fully consistent with general relativity. The same event producing two irreconcilable experiential realities. The question that kept theoretical physicists awake for decades after this was understood is, what happens to your friend's information? Information, in physics, means something specific. Not memories or knowledge, the physical information encoded in the arrangement of every particle that makes up your friend. Their exact position, velocity, quantum state. The complete physical description. The laws of physics, as currently understood, require that this information be preserved. Not that it stays easily accessible or readable, just that it exists somewhere and is not permanently destroyed. Physical information cannot be erased from the universe. This principle is taken so seriously that it's sometimes called the principle of unitarity, and violations of it would require rewriting quantum mechanics from the ground up. Now consider what happens from your perspective. Your friend's information, frozen at the event horizon, imprinted on that two-dimensional surface from your frame of reference, sits there indefinitely. Then Stephen Hawking shows up with a problem. In 1974, Hawking showed that black holes aren't perfectly black. Quantum mechanics, the physics governing the behavior of particles at the smallest scales, predicts that completely empty space isn't truly empty. The vacuum constantly seethes with pairs of particles that spontaneously appear and annihilate each other, too short-lived to be directly detected under normal conditions. Near the event horizon of a black hole, something different can happen. One particle of a pair can cross inward, while the other escapes outward before they can recombine. The escaping particle carries energy away from the black hole, energy that has to come from somewhere, which means the black hole gradually loses mass. This is Hawking radiation. The rate is unimaginably slow for any black hole of stellar mass or larger. A black hole the mass of our Sun would take around 10 to the power of 67 years to evaporate completely, a number so large it would require its own video to contextualize properly. For comparison, the current age of the universe is about 14 billion years, which is 10 to the power of 10 years. Evaporation timescales for stellar mass black holes are so much longer than the current age of the universe that for all practical purposes, they're permanent. But in principle, given enough time, Hawking radiation drains a black hole completely. When the black hole is gone, where did your friend's information go? If it came out in the Hawking radiation, scrambled, encoded in the correlations between particles emitted over billions of years, but still present, then information is preserved. The principle of unitarity holds. and quantum mechanics remains intact. But Hawking's original calculation suggested the radiation carried no information about what fell in. The radiation was purely thermal, random, featureless, carrying nothing about the specific particles that produced it. If that's right, the information is destroyed when the black hole evaporates. Unitarity is violated. Quantum mechanics, as written, breaks. This is the black hole information paradox, and it has been one of the most productive and contentious problems in theoretical physics for 50 years. It sits at the precise intersection where general relativity and quantum mechanics confront each other and disagree. Both theories are extraordinarily successful within their own domains. At the edge of a black hole, they make incompatible predictions. Something has to give, either our understanding of gravity or our understanding of quantum mechanics, or both. Whatever resolves this paradox will almost certainly be a piece of the larger theory physicists have been searching for, a unified description of gravity and the quantum world. The information paradox is not a marginal curiosity. It's a load-bearing crack in the foundation of modern physics, sitting right at the event horizon of every black hole in the universe. Cross the event horizon, which your friend did, in their frame, without drama, and the physics does something that has no equivalent anywhere else in the observable universe. Inside a black hole, space and time exchange roles. This sounds like wordplay, but it's a precise mathematical statement about the structure of space-time in that region. Outside the event horizon, in the space you and I occupy, time flows in one direction and space extends in all three. You can choose to move left or right, forward or back, up or down. Space is flexible. Time is different. Time flows forward, and you have no freedom in it at all. You cannot stop aging. You cannot move backward through the past. Inside the event horizon, the geometry of space-time rotates. The coordinate that pointed in the radial direction, toward the center of the black hole, takes on the character of a time-like dimension. It flows in one direction and cannot be reversed. Moving toward the singularity is not a choice you can refuse, any more than you can refuse to move forward through time outside the horizon. Your friend, having crossed the horizon, cannot stop moving toward the center. Not because some force is pushing them, because the singularity is their future. In normal space, you can stay in one location as long as you like. Time moves, but you don't have to move through space. Inside the event horizon, staying in place would require moving backward through the space-time coordinate that now points at the singularity, which is as impossible as moving backward through time is for us. The singularity is not a place in the way a city is a place, somewhere you travel to and arrive at. It is a moment in your friend's future that is completely inescapable from the instant they cross the horizon. It is, in the most literal sense the mathematics permits, when they are rather than where they are. Now let's ask, what is at that moment? What is the singularity, physically? The honest answer, and the important one, is that we do not know. What general relativity predicts is a point of infinite density, all the mass of the original star compressed to zero volume. But in mathematics, infinities often mean the equation is being pushed beyond the place where it can be trusted. They are usually not real features of nature. They are warning signs. At the singularity, the densities involved reach scales where quantum mechanical effects should dominate, but general relativity does not include quantum mechanics. It was not built to. So when we apply it all the way to the center of a black hole, we are using it in a regime where it has no reason to be complete. The infinite density predicted there is not a final answer. It is the theory breaking down and telling us it does not know what happens next. What does happen at the center of a black hole? No one knows. The physics is not there yet. The singularity is not the end of matter. It is the end of the current map. Whatever theory eventually unifies gravity and quantum mechanics will have to describe the interior of black holes without infinities. What that description will be remains entirely open. This is one of the most exciting frontiers in physics, not because the answer is known, but because it is not. Let's stay at the event horizon for a while longer, because it has been accumulating theoretical attention for decades in ways that go far beyond time dilation and redshift. In the 1990s, Gerard 't Hooft and Leonard Susskind proposed something remarkable about the nature of information near a black hole. The idea began as an attempt to understand the information paradox, but it grew into something much larger. Their proposal was this: all the information describing everything inside a black hole, every particle, every quantum state, every detail of everything that ever fell through the horizon, could be fully encoded on the two-dimensional surface of the event horizon itself, not stored inside the volume enclosed by the horizon, on the surface. A two-dimensional record of a three-dimensional interior. The analogy to a hologram is intentional. A hologram is a flat, two-dimensional film that can encode the information needed to reconstruct a three-dimensional image. The holographic principle proposes something similar for black holes. The three-dimensional interior is, in some deep sense, fully described by information living on the two-dimensional boundary. Susskind and 't Hooft argued that this might not be specific to black holes. It might be a feature of space-time itself. The observable universe, in this view, might be a kind of holographic projection, a three-dimensional experience fully encoded on a two-dimensional surface at the boundary of space. This is not a fringe idea. The holographic principle is taken seriously in mainstream theoretical physics. The strongest mathematical support came in 1997, when Juan Maldacena developed the ADS-CFT correspondence. In a specific mathematical setting, it showed that a theory of gravity inside a volume of space can be exactly equivalent to a quantum theory with no gravity living on the boundary of that volume. The two descriptions encode the same information. ADS-CFT does not directly prove that our universe is holographic, because the geometry it uses is not exactly the geometry of the universe we live in. But it shows that holographic duality is mathematically consistent and deeply useful. If the holographic principle is right, then the frozen image of your friend at the event horizon is not just a visual artifact. It may be where the information actually lives. The surface of the black hole may be where the story of everything that ever fell in is written. Not destroyed, not inside. Written on the horizon itself, in a language far more alien than any human writing, but in principle, complete. This changes the way a black hole feels conceptually. Not just a destroyer, an archive, an extraordinarily dense, extraordinarily strange archive written on a two-dimensional surface and maintained as long as the black hole exists. In 2012, a team of 4 physicists, Ahmed Almheri, Donald Merolf, Joseph Polchinski, and James Sully, published a paper that disturbed theoretical physics. What they showed was that 3 ideas about black holes could not all be true at the same time. The 3 ideas were: information escapes in Hawking radiation. A freely falling observer experiences nothing unusual at the horizon, and quantum mechanics holds everywhere. All 3 are powerful ideas. AMPS showed that together they create a contradiction. For information to escape in Hawking radiation, the particles leaving the black hole late in its life must be entangled with particles that escaped earlier. But quantum mechanics also says that an infalling particle should be entangled with its partner near the horizon. The same particle cannot be maximally entangled with 2 different things at once. Something has to break. AMPS argued that the smooth, peaceful horizon crossing might be the thing that breaks. If the required entanglement is violently severed, the energy released could create a wall of high-energy radiation right at the event horizon. Not the gentle, invisible boundary of classical general relativity. A firewall, intense enough to destroy anything crossing it. If firewalls are real, your friend does not cross quietly and continue inward. They hit a wall of radiation at the boundary and are destroyed in an instant. But that creates another problem. If a freely falling observer experiences something catastrophic at the horizon, then the equivalence principle, one of the foundations of general relativity, is violated. The choice is brutal. Either information is preserved and firewalls exist, damaging general relativity at the horizon, or information is destroyed, damaging quantum mechanics, or some third answer exists that physics has not fully found yet. Hawking later suggested that the event horizon might be less definite than the classical picture says, more like an apparent horizon shaped by quantum effects. Maldacena and Susskind proposed another possibility, that the inside and outside of a black hole may be connected through quantum entanglement, behaving like tiny wormholes. This idea is known as ER equals EPR, and it suggests that entanglement and space-time geometry may be deeply connected. None of these answers is universally accepted. The firewall debate remains unsettled. The horizon is where the tensions in our theories become most exposed, and the fact that physicists have argued about it for more than a decade shows how deep the problem really is. For most of the history of black hole physics, all of this was theoretical. Black holes were predicted by equations, inferred from the motion of stars and gas, and detected through their gravitational effects. But they were never directly seen. The defining feature of a black hole is that it emits no light, so the idea of photographing one seemed almost contradictory. The Event Horizon Telescope changed this. The project coordinated radio observatories across the planet to work like a single instrument with an effective diameter equal to Earth's. The target was the supermassive black hole at the center of the galaxy M87, roughly 55 million light-years away, with a mass about 6.5 billion times that of the Sun. In April 2019, the collaboration released the image, a glowing ring of radio emission from superheated gas surrounding a dark central region. The ring is not the event horizon itself. It is the shadow cast by the black hole, a darkness created because light from inside that region cannot escape to us. Around the edge of that darkness, photons are bent by extreme gravity, producing the bright ring. The size and shape of the shadow match the predictions of general relativity. A century after Einstein described curved space-time, we saw the geometry around a black hole behave almost exactly as the equations said it should. In 2022, the same collaboration released an image of Sagittarius A star, the black hole at the center of our own Milky Way, 26,000 light-years away. It showed the same structure, a bright ring around a dark center, the same basic geometry repeated much closer to home. These are not simulations. They are not artists' impressions. They are real images of black hole shadows, reconstructed from radio signals reaching Earth. The bright ring marks the closest region from which light can still escape toward us. Everything inside the dark region is causally disconnected from the outside universe. No signal from inside the event horizon can reach our instruments. There may be around 100 million black holes in the Milky Way alone, formed from the deaths of massive stars across the galaxy's history. Most are quiet, cold, and invisible unless they disturb something nearby. Each one of them has an event horizon, and from the outside perspective, each horizon freezes whatever falls toward it. There is another kind of black hole that makes the story even stranger. Most black holes are probably rotating. When a massive star collapses, it carries its rotation with it. As the star shrinks from an enormous sphere into a compact object, conservation of angular momentum makes the rotation become extreme. The result is not just a black hole. It is a spinning distortion of space-time. A rotating black hole has a different structure from a non-rotating one. The mathematics, worked out by Roy Kerr in 1963, describes a region outside the event horizon called the ergosphere. In the ergosphere, the rotation of the black hole drags space-time around with it so strongly that nothing can remain completely still relative to distant space. Even light is forced to co-rotate. The ergosphere is strange because it is outside the point of no return. things can enter it and still escape. Roger Penrose showed that, in principle, energy can be extracted from a rotating black hole through this region. A particle can split, one part falling inward and the other escaping with more energy than the original particle had. The extra energy comes from the black hole's rotation. This space-time dragging also affects time. A clock moving with the rotation of the black hole does not run exactly like a clock moving against it. The rotation distorts both space and time around the black hole, adding another layer to the already extreme time dilation near the horizon. Frame dragging has even been measured around Earth, although the effect here is tiny. Gravity probe B confirmed the small twist in space-time caused by Earth's rotation. Around a rotating black hole, that same effect would be vastly stronger. Step back now and look at the full picture. Black holes are scattered through the Milky Way in enormous numbers. Each one formed from collapse, violence, and extreme gravity. Each one has accumulated whatever matter fell too close. Gas, dust, stars torn apart by tidal forces, individual particles crossing a boundary they could never return from. From the perspective of the outside universe, every particle that crossed each event horizon is still there in some sense, frozen at the threshold, possibly encoded on the horizon, possibly preserved in a form we do not yet understand. The galaxy is full of these archives. Every event horizon is a kind of ledger, a record of what approached and crossed. But the word perhaps matters. The information paradox is not solved. Whether information escapes in Hawking radiation, is preserved holographically, is destroyed, or requires a completely different answer, remains unknown. What we do have is powerful evidence for the boundary itself. GPS satellites confirm that gravity changes the flow of time. Gravitational redshift confirms that light loses energy climbing out of gravity. The Event Horizon Telescope shows us the shadow of a region where light cannot escape. All of these point to the same underlying geometry. The theory says time stops at the edge, from the outside. The observations confirm that black holes have the predicted shadow and structure. The stopping of time follows from the same physics that makes GPS work and bends light around massive objects. Your friend is still there, from your frame. Frozen at the moment just before crossing, preserved in a fading image that technically never completely disappears. It simply becomes too dim to detect. From their frame, they crossed long ago, and continued inward to a fate physics can only partly describe. Both frames are real. Both experiences happened. Neither cancels the other. There is something quietly extraordinary about that. The universe allows two observers to have incompatible experiences of the same event, and both experiences are physically valid. The boundary between inside and outside is not a wall. It is a geometric threshold defined by what light can and cannot escape. Every black hole in the galaxy is an edge of time, not the end of time. Not a place where time is destroyed. A place where time, from one perspective, is frozen mid-step. The universe has been forming black holes for billions of years. Their horizons have been accumulating frozen moments since the first massive stars died. The black hole at the center of our galaxy has been gathering the fading records of infalling gas and stars across cosmic time. We sit 26,000 light-years from Sagittarius A star, surrounded by millions of smaller black holes hidden throughout the Milky Way. Around us, the universe is full of places where time stops from the outside and continues from the inside, simultaneously and consistently. The GPS on your phone confirms the geometry with every turn you navigate. The Event Horizon Telescope confirmed it with a shadow. Atomic clocks flown on airplanes confirmed it with differences so small they required extraordinary precision to measure. Time is not fixed. Gravity bends it. Extreme gravity bends it towards stopping. At the edge of a black hole from the outside, it stops. And somewhere out there, at every one of those edges, a moment is still happening. matter approaching the threshold, light fading, time stretching, a crossing that has already happened for the one falling in, and never quite finishes for the one watching from far away. The edge does not announce itself. It does not glow, vibrate, or feel like an ending. From the inside, it is not one. From the outside, everything that touches it becomes, in some sense, eternal, held at the boundary between the universe we can observe and the one we can only theorize about. That boundary is real. Its shadow has been photographed, and everything we know about physics says it does exactly what it sounds like it does. Time stops there.